Hey, Topping Airlines Math Industry, and we are going to take a look at the elevator physics, which is actually easier to explain than you think. So, when you ride on an elevator, you like to have fun, right? Well, when the elevator starts moving, and when you move up or down a floor, sometimes you feel like you can jump higher, sometimes you feel like you're more heavier, or sometimes your feet hurt because your feet are more heavier. Well, we're going to explain the whole elevator physics. So, in the past, we've been reviewing this stuff right here. The 4 forces that something can have when technically it is. We have an F of G, force of gravity, normal force, F of F, and the force being applied, which is what you're pushing up. But what if I told you that when it comes to calculating your weight inside an elevator, you're actually only taking a look at only 2 forces. Since the elevator goes up and down, we get to cross out F of applied and F of T. Yes, F of applied and F of T are in a different part of the elevator, but since it's going up and down, we're going to do force of friction, force of normal, and force of gravity. Sure enough, there is friction on the wires that lift up the elevator, but we're not going to talk about that. So here's what's going to happen. We're going to show 3 examples. Here's going to be the first. An elevator moving up at a constant velocity of 2.5 meters per second. The man has a mass of 85 kilograms. What does the man exert on the floor? That's what the problem should actually say. So if we draw a little picture right here, we have the elevator right here. We have an F of M and an F of G. And here is an awesome man who loves to have the elevator at. So when it comes to calculating the force of something, what we have to do is try to find the force of gravity, because we're trying to find what does the man exert on the floor, how much force does he have. So to find the man alone, we have to find his force, plus the elevator's movement force. So here's what's going to happen. To find the man in newtons, his weight, because that's his mass, 85 kilograms, all we have to do is use the formula F equals M times A. Fg equals M times A. So when we do that, we have 85 kilograms. But we don't know what our Fg is. But since we're talking about the man's weight and we're trying to get in newtons, right over here, we get to use gravity. So we have to multiply that by the Earth's gravitational acceleration, negative 9.8 meters per second squared. We're going to avoid the negative, and the man weighs around 833 newtons. So the man alone himself is 833 newtons. And that is the force of gravity when the elevator is in a constant acceleration. That's how much force the man is exerting on the elevator. Also, it would be 833 newtons if the elevator was not even moving at all. The reason why is when you have acceleration, your net force is going to, if you have a constant acceleration, your net force is going to be 0, because you only have a different net force if something is constantly changing its acceleration. So nothing is changing except like where you are. So that is the example if the elevator was moving at a constant velocity. So in this scenario, we're going to have the elevator move up a few floors. When the elevator accelerates upwards from 0.0 meters per second to 2.5 meters per second, find the temporary exertion on the floor. So we're trying to find the exertion on the floor in newtons. We already know that the man is going to weigh 833 newtons. What we have to do is find the exertion of the floor, the elevator in newtons. So what we have to do here is The reason why we say there's a temporary change of the newtons the floor is exerted on is because as you go from you're not moving at all to moving up, you feel like your calves or your legs hurt a little bit because the jerking of the upward force makes you a little bit heavier. And then after it, you feel it for a little bit. You don't feel it because the elevator goes into a constant acceleration. The only time you feel a jerk and you feel heavier is if the elevator is going up, but also the elevator might be going down. But the net force is not going to be zero. There is a net force when it accelerates to the Vmax, the maximum velocity. So here's what's going to happen. We have to calculate how much the floor is accelerating, the elevator's force along with the formulas. So we have to do F equals m times a once again. When we say that there's going to be 85 kilograms, that's the mass of the man, but we have to multiply that by 2.5, because that is going to be the accelerating, that's going to be the man accelerating up with the elevator. So how much temporary is that floor being exerted on? So the answer to this is going to be 212.5 newtons. And since that is the amount of newtons, or the weight, that's being added just by accelerating from 0 to 2.5 meters per second squared, we have to add the two. So the man's weight in newtons plus the mass, the weight added because of the jerk or the acceleration of the elevator, that's going to bring me to 1,045.5. 1,045.5. And that is the amount of newtons that is going to be temporarily impacting on the floor when the elevator accelerates upward. But what happens if the scenario was a little bit different? Assuming we say the same thing, but it takes the elevator to accelerate even faster down the elevator. So if the man is on the top floor and the elevator is accelerating down, moving down a bunch of floors at 3 meters per second squared, then that means that there's going to have to be some kind of change right over here. If we found when the elevator is going up, the man feels a little bit heavier of 1,045.5 newtons, then what we could say next is try to guess what it is. So the man is going to get in the elevator once again, but this time he's going to feel a little bit different. He's going to go down a few floors. So we know the man is 833 newtons, but we still have to calculate the addition to the elevator jerking from 0 to 3 meters per second squared. What we have to do is try to add that 833 newtons to the accelerating elevator, or the man's acceleration with the elevator. So F equals m times a. That's going to be 85 times 3. 85 times 3 is going to be 255. 255, but hang on. Since we have a vector of an accelerating elevator that goes down, what we're going to do is have a negative times 3. So what's 85 times negative 3? That will bring me to a negative 225. So that means the man's newtons and the man's weight would be decreased by negative 225 newtons when the elevator jerks from 0 to 3 meters per second squared down. But when the elevator reaches a constant velocity, or when the elevator is now a constant velocity, the elevator will go back to normal. The net force is going to be 0, and he'll go back to 833 newtons. So 833 subtracted by 255, that's going to bring us to, that would give us an answer of 578 newtons. So the man would feel 578 newtons going down when the elevator jerks and goes to 3.0 meters per second squared down the elevator. So that is the physics behind an elevator when going up, going down, constant velocity, and not moving at all. Thank you. I hope this video has helped you understand the elevator physics. Thank you for watching Top Finger Lines Math History. Like and subscribe.